Boy, I haven't seen a sound line either.
TDD 41.
Can sick her on that problem.
TDD, make it like a damn drawing for once.
Just to remind you, we're going to end this. I'm going to get a sign of whether or not this experimental camera is working. And if it is, then we're going to end it by us marching out to the front row and sitting there. Okay? And inviting people to crowd.
Oh, you're talking about afterwards?
Right.
Yeah.
Okay. Boy, I haven't seen the sound check.
Well, the hall's only half full. We'll be all right.
Yeah, I think we'll be okay.
We'll presume that whatever worked for the first session will work for the, we'll presume that whatever worked for the first session will work for this one.
Good morning. I'm Henry Fuchs from the University of North Carolina. I have the pleasure of welcoming you to this historic panel session in which we celebrate the 50th anniversary of what many of us consider the world's first interactive virtual and augmented reality system. The direct forerunner of today's AR and VR system with all its major components: the stereo see-through display, the untethered 6-degree of freedom tracking system, a full 3D rendering pipeline with stereo clipping and perspective. We have with us this morning Ivan Sutherland and many, maybe most, of his technical team from 50 years ago, the people who conceived and built this system. We also have with us another graphics pioneer, Fred Brooks, to set the stage, to explain to us the state-of-the-art of graphics in 1967, just before this revolutionary system was designed. After Brooks, we'll hear from Ivan Sutherland himself, and the inspiration for the project and how it came about, and a number of other stories I'm looking forward to hearing. Then we'll hear in turn from Bob Sproul, Chuck Seitz, and Quentin Foster. But first, let's start with Fred Brooks, who's both a computer architecture pioneer and a computer graphics pioneer. Among his many, many awards, Fred is the recipient of the National Medal of Technology, the Turing Award, and in graphics, the IEEE Virtual Reality Career Award in 2010. Fred?
Thank you, Henry. I have the privilege of doing the background talk, and I will remark that a lot of things happened before 1968, but three big things in graphics happened in 1968. The VR system you're going to hear about shortly, the first published paper on the frame buffer, and Doug Engelbart's highly interactive demo of all demos, it's been called. Well, I want to talk about another demo. The first computer graphics, the first interactive computer graphics, so far as I can determine, was done at MIT on the Whirlwind 1, which had a little 5-inch display tube, and it was a point plotter. This, I'd love to show you the video, but this is an overlay of multiple versions of that as the bouncing ball one changes the horizontal velocity of ejection out of at the left, and one tries to adjust it until the ball falls through the hole in the bottom. Now, Helen of Troy was called a face that launched 1,000 ships. This was the demo that launched 1,000,000 chips. It included real-time interactive. I forget whether you jiggled a dial or a key. It solved three differential equations at the same time, and there was a sound. It went bonk, 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 clunk as it went through the hole. It was done in 1949. I first saw it in 53, and as a Harvard computer science student, a group of us went down the river to see the wonders at the Whirlwind, and I knew then this is going to be important, and I want to do that. Cy Leventhal at MIT saw this demo in 52 and said, we can do molecular modeling with this kind of tool. It had many of the important components. So there was a light pen with which one could sense points. And well, let me back up here. No, I'll go ahead. The thing that was going on in parallel with Ivan's work at MIT on interactive graphics was going on at GM and was not well known. So the GM DAC system was proposed and contracted in 1960 and was in fact demonstrated in 1963, a fully interactive system. It turns out a GM research executive saw the MIT demo and went home and formed a team under Ed Jacks and asked him to address the styling problem. And so the interactive DAC system was built to do that. It turns out another person who saw that was a young chemist named George R. Price, and Price wrote an important paper in the 1956 Fortune magazine. It was an article called How We Can Improve Invention, in which he proposed essentially the system that GM later turned out to implement. Price was a strange genius. I hired him at IBM, and he worked for me about 4 or 5 years as we were developing our graphics offering for the 360, which was essentially a commercialization of the GM system. The DAC-1 project used IBM hardware, and GM Research had the responsibility for the software. It was a vector display. All the displays up to that point had been point plotters, including one on the IBM 704 that I first used in 56. And it included a 6-foot by 20-foot precision plotter because GM did their design in full scale in India ink on aluminum panels because they had dimensional stability. And there was a numerical control machine output from this, from which first clay models would be made and then dies, in fact, could be made. IBM commercialized this as the 2250 display unit, which was a mini computer with its own memory and a vector generator. We announced that in 1964. So here's a picture of the 2250. It was a 1024 by 1024, and it would refresh it up to 40 frames a second. Now, as the scene got more and more complicated, the picture got slower and slower, and it had a function keyboard, light pen, and was driven off any IBM System 360 channel. Now, Ivan we're going to talk about his system today, but the thing I find remarkable is that Ivan first envisioned two important visions, as George Price envisioned a thing that GM was sponsored. And his first vision was Sketchpad, which he then realized as his PhD dissertation at MIT. But the vision was we can do 2D mechanical drafting in a much better way and harness the computer to do what is really very painful on the drafting table. And then in 1965, the vision for VR, which we'll mention, and had many important students at Harvard and Utah, many of whom are here, and was a founder and key technical person in the Evans and Sutherland simulator company, graphics company, which is still making flight simulators and other simulators. So his original CAD vision, 62, I think was the first published version, was that we can do interactive 2D graphics on the TX2, which was a experimental transistorized machine at Lincoln Labs, a very fast machine that had a light pen. It incorporated important concepts of being able to make instances, and then you make a change in the master, and the instances change automatically, a forego of object-oriented programming and inheritance, and geometric constraint maintenance. So I wish I had a video of this, but I don't. But here's an example. If you sketched what you saw on the right and then said make it perpendicular and parallel, the system automatically did that for you, and so it would bring your lines in straight. If you had a scale drawing of 1/4 inch to the foot or whatever, and you put a dot and drew a line and said make it 2 feet, it would make it 2 feet in scale. Very important. Now, Sutherland's VR vision was one that turned me on when I heard it in 1965. And the key sentence, and this one is forever memorable, don't think of that thing in front of you as a screen. Think of it as a window. And through the window, one looks into a virtual world. Now that one sentence captures an incredible vision. Don't think of that thing as a screen. Think of that as a window. And so then the challenge in his famous 1965 speech that stunned me, I went home just amazed at the scope of this vision. One wants to be completely immersed in the virtual world. One wants to be able to move around in the virtual world, and the position of one's two eyes is tracked, and the scene changes appropriately in real time. As a matter of fact, the most important thing is that the world doesn't change except as a consequence of your motion. So there's no visible delay in the process. And then improve image generation until the world looks real. The user can directly manipulate virtual objects. The manipulated objects move properly according to real physics. The computer maintains the world model in real time. As you move something, all the other parts move appropriately. And, by the way, the virtual world sounds real, and the virtual world feels real. He even went so far as to say in the ultimate display, if you were shot by a virtual bullet, it would kill you. Well, now, what did the vision require? First, tremendous advances in display, resolution, color, stereo, field of view. Sound, do you have to do 3D, or can you get away with binaural? Haptics, can you simulate touch? Can you simulate friction? Can you simulate pain? Can you simulate heat flow? In modeling the virtual world, you have to be able to do the geometry, the texture, the color, the illumination, the optics of transparency, translucency, diffraction, etc., and the mechanics. In rendering, You've got to do tens of thousands of polygons in real time. You have 33 milliseconds to do them in. In tracking the position and the pose of the eyes. And in fact, the system then has to have a fast enough update rate that you're not conscious of it updating at all. It has to have so little latency that you're not conscious of any latency at all. And it has to be such that a person can buy it and use it. Now, the question, of course, that all this raises, if you can do all that, can make the perfect virtual world, so what? Is it of any good to anybody, or is it just for entertainment? Now, I won't go into that, but a whole lot of important things in training and in simulation have been done using virtual worlds, and I think a lot more will be. So the researchers have been pursuing Sutherland's vision ever since 1965, and today we will hear about the first realization of that vision. But I think the important thing in all three of these stories is the vision that came before the realization. The distinctive thing about Ivan's visions is he went on to do the realizations.
Next, we hear from Ivan himself. We could be here the entire session and just recite some of the awards that Ivan has received all these years, and it would not be enough time.
No, I'm going to tell about the best one right at the end of this talk. What a delight it is to visit SIGGRAPH for my very second occasion. First time was in Detroit. I was awarded the Coons Award. I knew Steve Coons very well. He had an office right next to mine at Harvard, was a very dear friend, and a wonderful man. He was on my thesis committee. He was the token mechanical engineer on my thesis committee. I, among other things, helped him get one of his two Model T Fords to work. Important to have two. You know, for airplanes, they call it the hangar dolly. It's the place of parts, where you get the parts from. So this all happened half a century ago. I've sometimes said it was not me, it was a much younger man who did all this. I just happened to share his name, not something you can change. Half a century ago, we turned on the first head-mounted display. Now, my role in this committee is to tell you about what brought up that. How did that happen? Why did it happen? What was the backstory? And as I tell this story, of course, you have to recognize that it will no doubt be embellished, because that's what we do. I'm going to start my story in 1948. I was 10 years old. I was a student at the Edgewood Elementary School in Scarsdale, New York. The school provided textbooks. We didn't have to buy them, but we were expected to cover them to keep them clean. And of course, my schoolmates all had very fancy covers from Columbia, from Princeton, from Penn, and other Ivy League schools. Even elementary schools in Scarsdale already had high ambitions for college. Now, my mother argued that our family couldn't afford the cost of such fancy covers. Fortunately, my father was a civil engineer, and he had blueprints, big blueprints, that would make terrific book covers. So they got cut up, and my book covers were all blue, and they had white marks on them. And those white marks represented objects that my father had designed. He was a civil engineer. his life work was taming the Snake River in Idaho. Many years later, my brother organized a tour for himself and me to go see some of the dams that were the subject of dinner table conversation when we were in high school. And we actually went there and had a personally guided tour by the foreman who ran some of these places. Some of the equipment in those dams, still running, had nameplates on it that were many years old. Now, when I was bored, I used to try and figure out what did these white lines on my books mean. And with some help from Dad, I learned how to read blueprints almost before I could read English, certainly before I could write English. And looking back, I realized that my family's alleged poverty was actually a carefully worked out plan, parental plan, to expose youth to education. I didn't like that much at the time, but I need to say now, thank you, Mom. Of course, the blueprints were orthographic projections, and so I had to mentally figure out what the shapes meant, and some of the shapes were pretty complicated. The water from a dam goes down through a penstock, which is basically a big pipe, and then it turns some corners and goes into a scroll case, which is a thing that looks like a snail that goes around the turbine, so the water goes into the turbine uniformly from all sides. And figuring out what that was in 3 dimensions was pretty tricky business. I wished I could look at it in other ways. Was it not till years later that I took a formal course in engineering drawing at Carnegie Tech, and I knew how to read engineering drawings, but now I had to make them. And I pretty much hated that, and you probably know that that's how Sketchpad came about. It seemed to me that having to erase those dirty marks on paper and leave all that eraser crud around was a bad thing. And if you could just have a nice clean computer to do it, the lines would come out straight and it'd make a nice drawing. And you probably know that that turned out to be my PhD thesis. I got a PhD from MIT in 1963, and occasionally people have called me the father of computer graphics. Well, you know, a person who has a mother and no father is in some societies rather looked down upon. Now, computer graphics may have a father but no mother, and I don't know how that fits in society. It's a little hard for people to be in that situation. Anyhow, as a former ROTC student, I had a 2-year commitment to the U.S. Army. But the Army was happy to postpone, after I graduated from Carnegie Tech with a bachelor's degree, the Army was happy to postpone my active service. So all the time I was at MIT Lincoln Laboratory, I was in the reserve Army. And when you're in the Army for a period of time, they promote you. So I was a 2nd lieutenant, but then they promoted me to 1st lieutenant, and I went to get my medical exam, which you have to do, and I asked the doctor what I had to do to pass this medical exam. He said, it's important that you have a body temperature of at least 90 degrees C. No, 90 degrees F, sorry about that. One gets confused when one crosses the Canadian border. But the good thing about being in the reserves was I got promoted to 1st lieutenant, and that makes a huge difference in an officer's pay. 2nd lieutenants are very badly paid, so when I finally went into active duty, I at least had a decent salary. The Army wasn't quite sure what to do with a fresh PhD in computing, so they sent me to the National Security Agency. And I think they did that because there were a great many computers at the National Security Agency, some of which Fred had a hand in building. Now, when I first knew about the National Security Agency, the chap who told me about it said, I'm sorry, I can't tell you how many computers we have, but suffice to say we measure them by the acre. Now, an acre of computers needs a lot more today than it meant in, those days. And I think the Army hoped that I would do something useful at NSA, and indeed I did something tremendously useful at NSA. I met another young lieutenant whose name was H. Quinton Foster, and he's sitting at the far end of the table down there. Army buddies, guys, Army buddies. He was really bright and he was really nice, but he did talk kind of funny because he was from the South. And Fred Brooks talks kind of funny too, but it's worth listening carefully. Well, I had quite a brief career at NSA. I don't know what I did wrong, but the Army decided to transfer me to the Pentagon. They gave me a job at the Advanced Research Projects Agency, which subsequently has had a D put in front for defense to make it clear who it works for. And my boss there was a man named Bob Sproul. No, not that one. That was Bob Sproul's father. So I'll call him Robert Sproul. He was my boss. He was my boss. Of course, at the time, I didn't know this Bob Sproul because he was in high school. I didn't meet him until much later as part of this head-mounted display project in which he was a key player. And we formed a lifetime friendship, which has been of great value to me. And thank you, Bob Sproul, for a lifetime of friendship. I often went to staff meetings in Robert Sproul's office. And I used to sit on his sofa next to one of the other office heads. He had 7 office heads, his direct reports. I was one of the 7, and the gentleman sitting next to me was a Major General by the name of Winnicky. And so I sat next to Major General Winnicky, and he always wore his uniform, and I never wore mine. I wore a business suit. And sitting next to a general at the same level in the organization chart may possibly have made me the rankest first lieutenant in the Army. I don't think that General Winnicky ever knew that I was in the service. Following a more recent Army tradition, he never asked and I never told. Well, I left the Army and I managed to land a position at Harvard University. Here we are. The right sweatshirt, right? Now, at that time, and maybe still now, I don't know about still now, but a person without a Harvard diploma was clearly not good enough to teach at Harvard. And sadly, my second-rate PhD came from some trade school on the other side of Cambridge. But fortunately, Harvard had methods. So I went to a faculty meeting and I was called down to the front, and it's not clear to me who was the person who actually handed me the degree, but let's say it was Dean Ford, handed me this wonderful honorary degree, the first one I'd ever had. Terrific. I was so proud. I called my parents and bragged, and there was a big parchment with seals on it, and so it was all written in Latin. I couldn't read it, but never mind. I was really impressed. Now I want you to think about, why did Harvard do that? I think it was a shrewd investment. Where's that coming from? I see. So we just don't worry about it, huh? Yeah. Okay. So it was a shrewd investment on Harvard's part. I figured that out about 3 weeks later when I got the first note from the Alumni Fund asking me for a contribution. And I have to tell you, Harvard is really good about keeping track of alums. Okay, they hit me up not less than 4 times a year. And in spite of the fact that I'm a bit uncooperative on that line, they still keep hitting me up. It's no wonder that Harvard has that enviable endowment. You need a lot of alums, and you have to keep good track of them. Well, while I was at ARPA, or maybe just after, I visited the Bell Helicopter Company in Fort Worth, Texas. And they were trying to figure out how to help helicopter pilots land in narrow clearings at night. And so they mounted an infrared camera underneath the helicopter, and they attached it to the pilot's equipment that he wore on his head, which had some prisms in front so he could see. And when the pilot turned his head, the camera turned in synchrony with the pilot's head. And that seemed like a pretty clever idea. Now, I remember that my host at Bell was a woman that I remember as Billy Abbott. No doubt she's dead now, but she was a very fine hostess, took good care of me, and she was from Fort Worth, where the West begins in Texas. Slogan is where the West begins. I guess that makes Dallas the place where the East ends. I wanted to buy a Stetson hat, a souvenir of Texas, and she helped me get a suitable, nice, good-sized hat. And it turns out that the crown of a Texas hat has folds and creases in it, which are different depending on where you come from. And so she insisted that I get the Fort Worth crease. Some years later, I spent a lot of time in Australia and became fond of the Australian Stetson, which is called an akubra. It's the same kind of idea, hot climate, big hat, right? You can tell from a Stetson where a cowboy hails from. I don't know if you can tell where a bloke hails from by the crown in his akubra. Now, my big contribution to the head-mounted display project was to recognize that we were just repeating what Bell Helicopter had done. But instead of a camera, we could substitute a computer. And that replacement allowed us to view a mathematical world of our own choosing. We could see anything we wanted from any angle, and that would make it easy to understand complicated shapes. It was an answer to my boyhood prayer. I could figure out how a penstock could connect to a scroll case. It seemed to me like the most obvious possible thing to do. And I knew it would work because Bell Helicopter had done some important psychological experiments with the head-mounted display. I think the best one was the subject was sitting in an office building in a comfortable chair with this equipment on his head, and when he turned his head, the camera, which was on the roof, turned its camera around too. And he was watching two people play catch on the roof. And he would turn his head so he could see, as the ball went back and forth, to see how the players were doing. And then one of the players threw the ball at the camera, and the subject ducked. And so it was clear that from his point of view, he was at the camera and not sitting in a comfortable office chair. And it was clear that we could have a presence in this strange world that we would create from the computer. There was no question whether the head-mounted display was going to work or not. There was just no question it was clearly going to work. Now, I didn't give the name virtual reality to this phenomenon. Help me out, Bob. Need the name. Jared Lanier is the person who named it. It was some years later, maybe as much as 10 years later. And I've always thought that that's rather a strange name. It's kind of an oxymoron. But maybe that was the point, that it was memorable for that reason. But of course, the head-mounted display that we built at Harvard was neither very real nor immersive. You could look at a small volume, you could certainly go around it all, but it was just glowing lines hanging in space. There was no substance to the object. A little later, you'll see some pictures from that time. Now, I'd like to end my talk with two stories that come from that period of time. And the first concerns Danny Cohen. Now, Danny Cohen was born in Haifa, and he came to the U.S. for an education, and he had a very keen sense of humor. And he also had some speech impediments, so it was a little hard to hear or listen to, understand, but it was always worth listening because he was a very clever fella. Now, we had this sword of Damocles, the mechanical head position sensor that was fastened in the ceiling and came down and mounted to the strap around the person's head that also had the head-mounted display. And that sword of Damocles could extend. It had springs in it to help support the weight. It could extend and contract. It was sort of two tubes, one inside the other. And it measured how long what the extension was. And it was pivoted in the ceiling, and there was a shaft encoder which very accurately measured the angle of the entire system at the ceiling. And there were two more shaft encoders for a universal joint, which was up there to measure how much turn that way and how much turn at the top. And at the bottom, there was another universal joint which measured how much tilt and how much yaw the person's head had. And these shaft encoders, if I remember, had 10-bit output, so there was quite a good precision in the measurement of the angles. Now, Danny was going to write the program that would figure out the projection matrix that we needed to show the image. And he reasoned that because there were only 6 degrees of freedom, his program would obviously have to compute the product of 6 matrices. And he sort of knew what the matrices were, but he didn't know what order they would come in or whether to use the transpose or not transpose and what sequence to put them in and so on. But his idea was, I'll write this program that multiplies 6 matrices together and then I'll tinker it into life. I'll just use my program debugging tool and change the order of things and so on. And I remember saying to Danny, there are too many possibilities, considering the transpose of the matrices and the signs involved and the order in which you're going to present them and so on. You're never going to tinker this thing into existence. You're going to have to think about it and actually figure it out so you write the program that will work. And that has always seemed to me a little microcosm of the difference between the tinkerer and the scientist or engineer. And you know, Edison was the consummate tinkerer. He figured out how to make an incandescent light bulb by trying every possible filament. And he was unsuccessful in getting electricity from Niagara Falls to New York City because he didn't have enough mathematics to do alternating current. He could only do direct current. And it took 2 European-educated PhDs to introduce alternating current to the United States. Steinmetz at GE and Tesla at Westinghouse. And there are many things that you simply cannot tinker into existence. And I think that this field, the field of computer graphics, is a place where thinking carefully about what you're doing and understanding what you're doing is now a key thing. And I'd like to say that Fred Brooks has been doing some real experiments to try and figure out how much reality is necessary and what the effect of different amounts of reality are. Now, my second story concerns research funding. Every academic research system scratches for money. At Harvard, we had the advantage of having Harvey Brooks as the dean of the Division of Engineering and Applied Physics, which has now become a school. It's now the School of Engineering and Applied Science. You see, the school expanded and the physics expanded to science, but it's the same place. Harvey Brooks was the dean of that, and by some magic, he had arranged that an Air Force PDP-1 would be stationed in Cruft Hall for the exclusive use of our group. A bunch of funny stories about that, which I'm going to miss over. But he also arranged for a grant from Bell Telephone Laboratories to pay $25,000 to the Perkin-Elmer Company to give us a duplicate of the very same head-mounted equipment that Bell Helicopter had constructed by them. Bell Helicopter had had substantial funding and had induced Perkin-Elmer into designing this fancy optics, and we simply bought serial number 2. And the CRTs stuck out way to the side. And if you ever wonder why that was, it's because the pilot had on an APH-5 crash helmet, and the CRTs had to clear it. Well, Fred Brooks was a really wonderful guy. He was on the President's Science Advisory Committee, had a lot of contacts in Washington, and he was able to produce funds. And somehow I got wind of the fact that the CIA was willing to place a grant at some reputable university. Perhaps they were willing to do that to make up for some supposed past misdeed, I don't know. But I thought that Harvard was a pretty reputable place, and so I stuck my hand up and says, I'll take it, I'll take it. I think it's time to show the first slide. Fred, will you? So I got a telegram which says you got a grant for $80,000, if my memory serves me, from the Central Intelligence Agency. That was terrific. On the other hand, the old mole got wind of this grant. Can I have the next slide? The old mole, I looked up in Wikipedia, and I'll quote this directly. What the old mole Wikipedia says was a radical, new left-oriented underground newspaper published in Cambridge, Massachusetts from September 1968 to September 1970, 2 whole years. Now, maybe that's because you shouldn't wrestle with Harvard. I don't know, right? But there was some controversy about this, and so Dean Ford organized a faculty debate to see about the propriety of Harvard taking money from the CIA. The debate was to be held in University Hall, and big place, plenty of room. I went. There were to be 8 senior Harvard faculty to speak, and they would be alternating. The first one would be against, the second person for, and then con and pro and con and pro and con, and Dean Ford saved the last slot for himself. And in his final argument, Dean Ford pointed out that the source of funding is entirely irrelevant. The only thing that matters are the conditions of the grant. And the condition of the grant from CIA was no classification, publish anything you want, here's the money, we want to report occasionally. More funny stories about that, but we want to report occasionally, and that's all. Great conditions for a grant. And Dean Ford pointed out that Harvard should understand that only the conditions of the grant matter, because after all, a large fraction of our endowment came from New England sea captains who'd grown wealthy in the triangle trade. Now, I personally got a great deal out of the head-mounted display project. The most important thing I got was comradeship with my colleagues, who turned out 50 years later to join this symposium. Another thing I got out of this project was my second honorary degree from Fred Brooks at the University of North Carolina. Thank you very much, Fred. I appreciate that. And I may say that the University of California is much more gracious about dunning money letters than Harvard. Another great thing I got out of this was I got to know Fred Brooks. Fred had long been a hero of mine, and now I'd like to say that he's become a friend. Well, of course, I have to tell you about the future I saw for virtual reality. I never thought much about the future. You know, I couldn't imagine what people would do with this thing, and I just did it because it was interesting and seemed possible. But it's changed my life dramatically in two ways. The first way it changed my life dramatically was that I met Chuck Seitz, who's here today. And Chuck taught us how to design electronic equipment. He was an MIT graduate student at the time, but he joined the group and explained how we should use the fledgling little chips that you could buy then and mount them on printed circuit boards and actually build this system. And he encouraged us to build it as a pipeline with a stoppable clock in each stage. So it was, in fact, asynchronous. In 1988, I gave a Turing Award lecture when I received that award, and the best part of a Turing Award is that you get to publish the lecture that you wrote in Communications of the ACM, which is a refereed journal, but you get to put your paper in without referees. Whoopee! So I took the opportunity to publish kind of a radical technical paper called Micropipelines about asynchronous hardware. And that paper got referenced a lot. It revived interest in a number of places in asynchrony. So thank you, Chuck Seitz, for my second career. I got something very nice out of that early in the sequence of asynchronous conferences. I met this very wonderful woman named Marley Ronkin, who is now my research partner and my wife. Marley is the director of our Asynchronous Research Center at Portland State University. By the way, grants would be welcome. Now, the second important change to my life came when the Virtual Reality Society gave me its Founders Award in 2015. This was a gala event held in the very same Hollywood theater where the Academy Awards started. And like the Academy Awards, the Virtual Reality Society usually honors creative people, the people who put content into the images that we see. The awards are for the most compelling, the prettiest, the most realistic, all kinds of things that have nothing to do with technology. And one for what is the most fun game to play, and I'm all for fun. So I had to give an acceptance speech. What am I going to do? Well, you can see that acceptance speech on YouTube if you look for it. And what I did was to point out that I had started a tool, kind of like the movie camera. But that tool alone is of no interest whatsoever. I compared that to the Gutenberg printing press. And I said the important thing about printing is what got into the print. And there were people like Shakespeare and Dickens and Hemingway, the great authors, who made it worthwhile to read the printed word. And those guys in the Virtual Reality Society are doing the same thing for us. But the most memorable part of that award was that the audience was tweeting away, so on. And they decided that I should be called the godfather of virtual reality. Now, a father, as anyone who has children knows, has very little authority. But a godfather, now, that's a title with real clout.
Well, after that, I'm not sure what's left for the rest of us to do. We're going to very briskly go through a little bit about the project itself. You can find it all in papers from the Fall Joint Computer Conference in 1968, but we'll try to embellish it with a little bit more personal patina. So, but to set the context, here's a diagram of the system we built. There's a head, the sword of Damocles, the boom that Ivan described is shown attached to the head with shaft encoders to measure position. It's connected to our PDP-1, our personal computer that was so wonderful. The next step was to provide or send image or line drawing information to a matrix multiplier, which Chuck Seitz built, and he'll describe that briefly. This was all in fixed point arithmetic. Ivan in Sketchpad figured out how to do scaling on with fixed point arithmetic, and we had to do that here. There was no floating point, certainly no floating point hardware. The notion of matrix multiplication to do orthographic projections was well understood at the time. Larry Roberts and others had been doing it at MIT, at Lincoln Lab. Next came the clipper. This was the perspective division, again, done in hardware. This was an algorithm that Ivan and Danny Cohen worked out, and we built some hardware to actually implement it at reasonable speeds. And then digital coordinates of line endpoints were passed to an analog line generator, which I believe we bought from, or was donated by Adage, which was at the time making a very fine vector graphics display, and then the rest of it was their analog gear. Ivan came in well, actually, he didn't come in one day. I came in one day to the computer room and found a wonderful little lucite cage, inside of which was about maybe 2 or 3 cubic feet, inside of which was a whole bunch of transistors that had been built by our technician. This was Ivan's design for the equipment to drive the CRTs that were on the head-mounted display. It required 300-volt deflection signals. These were electrostatically deflected CRTs. And I think the reason it was in a lucite cage was so that when something blew up, you could see what it was. Now here's a piece from an early memo that Ivan wrote in May '67 as we were beginning to get the structure of this system together. And the reason I put this up is to point out that one of the things that Ivan did with his research projects, perhaps even before this one, is make sure everything got written down. And it didn't matter whether you later superseded it with another idea, but it was an important communication device to write it down so everybody on the team could see it. And this is one of the first contributions to that, and you'll see in the upper left-hand corner, I think it says, to the 3D display file. And in fact, this volume of documents came to be known as the display file, a deliberate pun. Well, so let's talk very quickly about the head position sensors. Ivan has already described to you the mechanical one, the sword of Damocles. The sword was simply the boom and the mechanical arrangement in its measuring device. It was not a name for the whole system. So Ivan, do you have any comments you want to add?
No, that's if you look on the web, you'll find that our whole system, which we call the head-mounted display system, is often called the sword of Damocles. This is a little like calling, New York the United States.
All right. But we had another one. So this is a picture of Quint, I believe, with the sword of Damocles. This was from the paper. You can go find it. But we had another one, and that was Chuck.
I wanted to get you in the mood of the 1960s. Can you hear okay? This was Ivan's personal computer in the 1960s. This was the famous TX2, which was built in Group 23 at Lincoln Lab. And of course, even on the campus, we knew all about what they did at Group 23. And so I was very much wanted to work there. So after my first year in graduate school, I applied for a job, and they gave me one. It didn't pay the most of the jobs I could have gotten, but it would have taught me the most. And it was at Lincoln Lab that I met Ivan. You can see this is quite a good-sized computer, and it had switches and lights. I think it had something over 10,000 lights as indicators. because this machine belonged to the engineers, and they they made changes to it every Wednesday. So you see, this was heaven on earth for me. I loved designing logic, and but with my relative inexperience and the expense of the components, even the early microelectronic components, I didn't get to do as much of it as I wanted. But Lincoln Lab was heaven, because they not only had all these people who knew about designing logic, they had a shop where they would build things. Of course, no fun to design it if you don't build it. And so I was eager to learn. My assignment was to design a new interface for one of a new display for TX2, and I made the mistake of finishing that design in about 2 weeks. So I was at loose ends for other things to do, so I went around looking for things to do. Larry Roberts was there, and he had this idea about making a three-dimensional wand that worked by pulse ultrasound. It didn't work very well because it was kind of sensitive to too much noise in the room. And the thought was that maybe one could do this better using continuous wave signaling, and that was for Ivan's head position sensor. So just in brief, it was 3 transmitters on the head and 4 receivers overhead, 12 measurements, and 3 different frequencies. I don't remember who did the analog parts of that, but it was a very simple. This is not gaining me very much design experience, because this design time for the interface logic there was only about a few hours. And it's very easy to, let's see, this thing probably also points. Does it point?
It's supposed to. Just punch on.
Oh, there. So you see the oscillators up here, each running at 64 times the frequency, counting down by 2 to the 6th, and that, as long as you are controlling the transmitter, it's very easy to extract the phase of the received signals. And so here it is with my friend Quint here in his voltage-resistant mode, bravely wearing the high voltage on his head. This is, oops, here. Will it let me go back?
Yep, it's the upper
Yeah,
one.
there it is. So here's the sort of Damocles, which always hangs over your head, except if you disconnect it. And this is we called it the shower stall, even though the direction of radiation was upward. And you can see the gadget on Quint's head there. There isn't enough resolution to read that sign, but I believe that's a sign that Ivan put up there that admonished undergraduates using that area not to use this as a chin-up bar. Anyway, the very bright Harvard undergraduate named Bruce Baumgart did the math, the analytic math correctly first of all, and then wrote the program to figure out the integer part of the distance. You can see in the background here, oops, I'm sorry, this is a couple of racks of equipment, parts of the matrix multiplier and clipping divider. So, of course, one of the things we had to do is learn how to build digital hardware in a university. Harvard was quite receptive to that. This was all done when Ivan's office was in the Aiken Computation Laboratory, and they had some old machines down there, beautiful things. We were able to just buy logic cards from a company called Monitor, no longer exists, quite small scale integration. and they were put into card cages that had 28 cards in a cage, and then put the systems together. The matrix multiplier, about 300 cards, and the clipping divider, I think, about 280. It claims here that we didn't do any CAD. Not. All of this was designed using one of these plastic logic templates. See some of the nice drawings here. And then Quint wrote a bunch of programs to do all the wireless management, and they could use those to drive the wire wrap machines that wire wrap the backplanes. So Ivan and I learned much later that if you invest a lot of time in CAD tools for a given project, it doesn't benefit the project you're doing, it benefits the next project. So fortunately, we didn't have to do too much of that. And here we were essentially imitating the style of design that was used at Lincoln Lab, Group 23. So let me tell you briefly about this matrix multiplier. It, of course, transforms a stream of points. These are points in the form of X, Y, Z, W, for which you say, what's that W there? X, Y, and Z are probably the normal Cartesian coordinates. Well, the W is a scale factor for homogeneous coordinates because these matrix elements and the coordinates were 18-bit ones complement signed integers, no floating point. For example, if you set W to half, that's your basic unit of measure. If you set it to 0, you can put things infinitely far away. And you can read a book by Newman and Sproul, learn all about it. Of course, because the PDP-1 was 18-bit machine and delivered 18 bits at a time, what we could do for each time we received a coordinate, we could do 4 parallel accumulating multiplies. And so that was the organization of the machine. 4 identical column units. We're very lazy. Got a lot of stuff designed with minimal time. There were, of course, all the usual additional functions for loading the matrix and getting the result out in multiple forms and various diagnostics. So performance ended up being about 5 microseconds per point. That was the spec that Ivan had reached at the beginning, because, of course, the points can be, lines can have unique endpoints, so they can have shared endpoints. So on average, between 5 and 10 microseconds per line. This is fairly good performance for 1968 using these inexpensive integrated circuit modules. One thing I note about the whole system, though, is that with the pipeline, the internal parallelism in the individual units, extensive use of parallelism and concurrency. You see, we really were pushing the limits of performance for that period. And when you are pushing the limits, one thing you use is concurrency and parallelism, and the other thing you use is specialization of function. So just as you find in today's graphic chips, if you reverse engineer one of today's graphic chips, you'll find a lot of these very same characteristics. So let me turn this over now to my young colleague,
Yes.
Bob.
And indeed, I was the youngster on the project. I was an
I should mention that you are, I think, one of 2, at least, undergraduates. So
Right.
those of you who are students, I think should take inspiration from this, that undergraduates can come and talk about their world-famous system
Well, and since
50 years later.
Since we're on this topic, the National Science Foundation has for many years championed a program called Research Experiences for Undergraduates. This was not done with that. This was done with ordinary Harvard money. But it's a marvelous program, and it's been enduring, and one of the things that is very important about bringing up the new generation. And certainly I benefited a great deal from the opportunities that I had on this project. This is me at a science fair project. I was looking for something young. I guess I'm young enough there. In the spring of my sophomore year, this new associate professor came to Harvard and offered a computer graphics seminar, and a friend of mine managed to find it advertised on a bulletin board. That was the kind, you know, with cork and paper stuck to it with thumbtacks. And so we all traipsed up and got interviewed by Ivan, and some of us got, I think almost all of us got into the course. And we had great fun with that PDP-1, our personal computer. But Ivan recruited me to join the project, and so I started out in the summer of 1967 working on the project, and worked on it for the rest of my senior year and then the following summer as well. And ultimately in August 1968, the whole thing was packed up and shipped to Utah. Things had just barely gotten working at the time. So clipping, I'm not going to spend a lot of time talking about clipping. Clipping was something, though, that we didn't really have an algorithm for at the outset. And we were a little bit gun-shy about doing divides because there was no, hardware for doing divides was slow and expensive. And it was clear you had to do a divide if you wanted things further away from the eye to be smaller than the things closer to the eye. But the key algorithm came out of really work with the whole team, but Ivan and Danny Cohen, I think, were the main contributors. It's one of the reasons why in our graphics book, William and I called it the Sutherland-Cohen clipping algorithm, because the real algorithm, the idea of using midpoint subdivision and classifying the points of each end of a line or a subline relative to the edges of the window was the key idea that was ultimately embedded in the Clipper hardware. So the hardware computed endpoints. It then was able to compute a midpoint and decide whether the new point was a point you wanted to keep as you were searching for the intersection between the line and the edge of a window. And this was some of the hardware. Once you did the clipping divide, you then had to also scale it. You then essentially got a fraction or a location relative to the size of the window, but then the question was, what do you have to convert it to screen coordinates to give to the analog, digital to analog converter. So the hardware on the same hardware, but was used in a configuration on the right in that diagram to do actual, now we really are doing divides, but we're doing a multiply at the same time. So to do that ratioed calculation was essentially a combination of a multiply and a concurrent, a divide and a concurrent multiply. So today, you wouldn't even look at this as an interesting way to organize this because divides are cheap and you just do them. Here's, the Clipper turned out to be a fairly simple state machine, and it actually had 2 cycle times, as we're using the stoppable clock idea. If you were going to do an add, you took a little bit longer. So the thing I would like to remind you, and starting from the outset here where we talked a little bit about the overall diagram, that the pipeline that we were playing with then is pretty much what you see today, although the parts, of course, are implemented entirely differently and embedded in different ways. The project turned out to be a pretty good prototype for or first version of what Evans and Sutherland ultimately made as their flagship display, the LDS-1, their very first display that did this as a product. And the final thing I'd like to point out is that Chuck talked about the 600 or so cards in our system. Today, they would all fit on a piece of silicon that is small enough it would fall through a hole in a printed circuit board. So 50 years of Moore's Law really does amount to something. So now I'd like to move on and to give it to Quinn to talk a little bit, and last but not least, because he's the guy with the 3 kilovolts on his head, and 300 volts were for deflection. There was 3 kilovolts to get the electrons from the hot cathode down to the surface of the CRT. So Quinn, it's yours.
Thank you, Bob.
Thank you. I want to mention, because we have very little time left, that if you want to ask any questions, send email to that address that's on the lower right. And Laura in the front is monitoring these, and so whatever time we have for questions, we'll take from whatever you submit. And by the way, this is being live streamed, so we've gotten at least 1 question from the Netherlands. that we'll bring up. So Quentin, take a few minutes, please.
Okay. I'll go as quickly as I can. I want to talk a little bit about wearing the display, excuse me. And we've talked a good bit about tracking. I'll flip through that quickly, and I want to talk about the users, and I'm going to get Bob to help me a little bit on that. So here is, you're looking at all these people up here who have been famous for their entire career. Some of us, lesser people, use the Andy Warhol algorithm and have our 15 minutes of fame. This was my 15 minutes of fame. So how much voltage was up there? I'll talk about that in a few minutes. But putting this display on, putting this headset on, I was a little bit apprehensive about this. Ivan, I think Ivan, you designed the high voltage, or was it you and Chuck? Anyhow, I think Ivan had designed the high voltage drive for the CRTs, and we had a technician who had wired this up. So I remember very distinctly having a discussion with the technician, who's going to put this thing on? And I lost the argument. So I ended up wearing it. I wasn't scared. I was apprehensive. You know, you've got to wonder if you're a little nervous about the design and all of that. But it turned out not to be a problem. What did happen was, over the period of time, this voltage grew. As you pass on, you think it's 3,000 volts. Well, and then it became 5,000 volts. And eventually, I was telling people I had 10,000 volts on each side of my head. No, it was only 3,000. At least I think that's what it was. When we were putting this talk together, I made a snide comment about, well, you know, my memory's not very good. I can't remember much about all of this. You guys are going to have to help me. I had 10,000 volts on my head, and Bob immediately came back and said, Quint, no, I don't think it was 3,000. I mean 10,000, it was 3,000. So anyhow, here you've got a view of the headset, and you can't quite see that there are prisms in front. But the next slide should show not a very good view. This is one that's sitting in my basement, picture sitting in my basement. But you can see the, which one is there it is. You can see that there are prisms there that you can see through. And I'll show you a picture of what things look like on the display. This is the ultrasonic, even though the original paper said it was the Sword of Damocles. This was the ultrasonic. I remember almost nothing about wearing this. But, you know, if you had asked me what was it like, I'd stretch. I wasn't even sure I'd had it on. But here we have an existence proof that I did, in fact, wear the ultrasonic headset. What I do recall vaguely was I didn't wear it very much because my recollection, vague recollection, is that it wasn't as accurate as the Sword of Damocles. And I'm going to let some of these other guys talk a little bit about that also if they'd like. But it had some problems. I also sort of remember that maybe it was up on the front of your head rather than attached to the top of your head, and that may have had something to do with it. But as I say, I don't remember a lot about it. Chuck has talked about the design and the software written by Bruce Baumgart. It did work, obviously. This is the Sword of Damocles, and I think the important thing to remember, as Ivan has already pointed out, the Sword of Damocles was the tracking device. It was not the entire head-mounted display, etc. It was distinct. Maybe some of the reason for why people think the Sword of Damocles was really the whole project was if you wanted to put this thing on by yourself, you probably had to put the Sword of Damocles, attach it to the headset, and then put it on. I remember using this more and moving around to see one or two of the objects that we had. And I think Bob had indicated that it put some pressure on your head. I don't remember much pressure. I remember it being very easy to use. Who are some of the early users? Well, you're looking at many of them sitting right here that wore this headset. I distinctly remember Todd Whipke doing some molecular modeling. What I don't recall, and you guys can correct me, I don't remember whether we actually saw that with the head-mounted display, or was that just with the adage display? I think it was just with the adage. Bob, do you remember?
Well, so I think the image that you see in the fall joint paper, we
Right.
actually did put up on the head-mounted display. But I wouldn't call it so much modeling as just a display of a molecular wireframe molecule.
Right. Danny Cohen's room, I'm going to show you that. It wasn't really Danny Cohen's room. As Bob said, Danny Cohen developed the Hello World of head-mounted display, and I'll show you a picture of what that was in just a second. Danny also wrote a carrier landing simulation that I remember, but that was much later. I don't think that ever got used or seen on the head-mounted display. Ivan has talked about the work, the funding that was done. They had to give a final presentation, and Stuart Ogden actually gave that. I think Ivan and I had left Harvard at the time and had moved out to Utah. Bob reminded me that Yaakov Agam, I'm pronouncing it right. I'm going to let Bob tell you a little bit about Yaakov and what he did.
So Yaakov Agam was a visitor, an Israeli artist who was visiting Harvard in the summer of 1968. He's a kinetic sculptor. He likes to do sculptures that move, often in the wind. Not mobiles, but usually pedestal-based objects. He was quite interested in this and came over and spent a fair amount of time with the head-mounted display on, peering around, looking at static objects. But the reason I mention this is here was an artist who was kind of interested in at least figuring this stuff out fairly early on.
Okay, let's, as I said, this wasn't really where Danny Cohen lived, but he generated this object, which was one of the things that we could see using the head-mounted display. And if you take a look at this, you can see that the N, E, S, and W are slightly offset from the outline of the room. And notice also this is all line drawing. There are no hidden surfaces here. I'll skip that one. Bob put this picture together. When you were looking through the head-mounted display, this is what you'd see. Bob jimmied this up a little bit from Chuck's picture of the TX2. But typically you'd look through this and you could see the PDP-1 or you could see the racks behind you. But if you had one of the tracking devices on, you could move around and you could actually get between the letters, N, E, S, and W, and you could look back at them. So you didn't have a lot of room to move around with the sword of Damocles on your head. You maybe 6 feet or something like that. So where is this device now? Well, it moved to the University of Utah. I think there was some use of it at the University of Utah. I won't go into that. And it now is resting at the Computer History Museum in California. So I'll turn this back over to Henry or any of the others that want to add to my poor recollection of wearing the head-mounted display and the work that I did. Henry?
Thank you, Quentin. We just have a few minutes, and we have a bunch of people that have emailed questions. But before, does anybody want to make any comments, or should we go to questions? So several people from different places asked about how did the Sword of Damocles get to be the name, and does anybody remember? And by the way, among the people, Anthony Steed, who's here from London, and some people from family Ronken from the Netherlands, related to Marley, emailed this is what it says here, emailed a question about, tell us about the name of the prototype and how did it
Is
came.
the first name of that Ronkin Paul by any chance?
It said family of Ronkin.
Family, okay.
Yes.
That's their email, all right. They're a fine family. Before I married Marley, I went to visit them. I didn't think it was appropriate to ask her father for permission, but I did think it was polite to go at least visit them and tell them that my intentions were honorable. Now, I named the Sword of Damocles the Sword of Damocles. And I believe that that's an ancient reference to the sword that hung over you if you were not going to tell the truth. I don't know exactly what the reference is, but that's my fault that it got that name. And it was quite an intentional reference.
Right, so are you happy that now you don't have a famous name for the entire system and the entire country is called New York? All right, so another question that came is somebody, I'm trying to think of who wrote this, and I can't find who wrote this. If you had to do this all over again, and you were back there and you could have magically changed something in the design, would you have done anything differently?
I think engineers have to work with what's available. You know, you didn't have microchips available at that time. You couldn't, build a special purpose chip. So we did what was, and basically we listened carefully to Chuck. Chuck was the expert, and so that's what we did.
So can I offer?
Please.
So I want to add another piece, which is, this was Ivan's genius. He didn't talk about it much, but there was a fair number of make-buy decisions here. We didn't try to build the optics. We didn't try to build an analog vector generator and make pretty-looking lines. We focused the construction and new work on a specific piece of the problem that was not well understood, and used other people's work and other much more effective techniques to fill in the gaps.
Another question came up. Were you planning at the time, in 1968, any of you or Ivan, of doing follow-up work on this? I mean, I know a few of the answers to this, but other people may not know. What was your thought about the next system or an improvement in 1968?
I really didn't think very much about the future. Who would have thunk 50 years ago that we'd be here at this conference? I certainly wouldn't have. And this was pioneering work that didn't actually do anybody much good. The pictures that we saw were all pretty primitive, pretty understandable. There wasn't any brilliant new insight that came out of this from a scientific point of view. But I think... I'm sorry?
Leventhal's protein.
So I have a different answer to that. Okay, that guy, this guy, and this guy immediately went to Utah and put full force into a startup. A startup is an all-hands-on-deck kind of company. You ain't doing research, at least if you are, you don't admit it. And you try to build a product. And I think this project contributed a great deal to that, but it didn't further, none of that furthered VR.
I was going to add something similar to what Bob just said. What came out of this, Evans and Sutherland, and the employment of a number of people in Utah. And I remember Ivan telling me one day, once we got some stock options, this will put your children through school. And I laughed at him, it's never going to happen. Well, indeed, it did. It put at least one of our daughters through school. The other one eventually came back much later to go to school. But thank you, Ivan.
So I've got to inject one personal story in this that I didn't think I would be doing. So I heard about this in 1969 while taking a course at Stanford from Alan Kay. I heard, he showed me this 1968 paper, and I thought it was the greatest thing I had ever heard about. And thanks to Alan, I made a beeline for Utah And of course, what I found is there was this company already started that took up a lot of Ivan's time and a lot of Dave Evans' time. But there was this head-mounted display there. And there were other things that were brewing. There was a guy who was working on a real-time raster image generation system, a guy named Gary Watkins. And I remember thinking this was something that you poured in polygons, and out came video. And I remember thinking, wow, if we could only like hook this up, to a head mount, then you would get like realistic images. And then a couple of years later, Ivan said something to Bob Burton about doing some kind of a tracking system that was called the Twinkle Box, and had the idea of maybe you could walk around an entire room and track with some lights on your head. So I remember thinking, now I was, young and foolish, but I remember thinking, wow, if you could just make that work, walk around the room, have raster images in your head mount, that would be so cool. Okay, so at least the inspiration, I think, was already there in the early 70s. Now, I think we only have time for like 30 more seconds, so I've got to choose carefully. What I want to thank is a whole bunch of people: Ren Ying, Masahiko Inami, David Nagel, Daniel Lethings. I mean, all these people, Bhuvan, somebody from New Zealand, Christian Gruel. I mean, all these people are sending questions, and I will at least send the questions on to the people here on the panel so that you will see how many places and people are interested in, from Netherlands to New Zealand. But we have a special treat to end this panel that only a few of you know about. Is there a drum roll here? Do I hear a drum roll? Okay. We have a group here from Google, Paul DeBevick and friends. Paul, are you here? Is that yes? Yes. So, and they're bringing their latest experimental light field camera to record this historic event. We spent a lot of time in this space yesterday. It turns out recording a bunch of people in back of a table is not such a cool idea, especially if they have black in back of them. So what we're going to do is go to the front row. You will see the front row has like a half a dozen seats empty. And if you want to be part of this historic 3D light field photo, come crowd around the front, and you'll be all, but you have to stand still and listen to Paul DeBevick. Thank you, one and all, for coming to this historic panel.
All right. Thank you very much, Henry. Thanks our panelists. That was an amazing panel. Thank you for this opportunity. The original idea is that we would just kind of do this in a little private setting outside of the room afterwards. So if there's any equipment problems or we need to adjust things or anything, it's all like very cool, low pressure kind of situation. So welcome everyone to our public light field recording here. We are very happy to have our esteemed panelists. We have 6 seats reserved for them right here in the middle. We're going to have a couple of lights turn on. And what we have is this is part of what we are showing in the immersive pavilion all week, which is called Welcome to Light Fields. I'm here with Daniel Erickson, who's one of the big contributors, programmers to the project. And what we're going to do is we're going to basically spin GoPros around in a sphere, try to capture all the rays of light coming into this sphere. And then in a headset, which maybe by the end of the week we'll even have running in the booth, you can basically move your head around, see left and right, back and forth, and actually have a super 3-dimensional virtual reality photograph that you can see with a 6 degree of freedom tracker, which seemed, Henry thought that would be appropriate for the subject matter for today.
And you don't have to wear 10,000 volts.
And no. Okay.
Or even 3,000.
So this is built out of some consumer GoPro cameras. We don't have a whole ball of them, so we have to stay still while it swings around. We're going to do the first one at a faster setting just to make sure that we get something, and then if that one goes well, we'll do a slower one. So we'd like to have all of these seats filled up here, and let's see here. Let's try to get, let's spread these doors out as much as we can. And let's see. And actually, maybe we can get these on the tape marks there, possibly.
Yes. We need to have some people fill. I think this looks like it's on.
Okay. Okay. All right. Are we on full blast on the lights? Let me just double check that we're all the way up here.
How many of the people around will this thing take? You'll go all the way around, right?
Yes. So we'll get a 360.
People could be here, like.
Yeah, people can be around there. So the idea is you need to stay still. So the cameras have about 120-degree field of view. So if you're in the half plane that the cameras are pointing toward, be as motionless as possible. That's the idea. Okay. So let's go ahead. We're going to set a setting here. We're going to set this thing to go around. I'll set it to go around twice so that we have 2 chances. All right, we're going to hope that all of this works. This is, I think that was another theme of the panel.
Less than 3,000 volts.
Yes. Okay, so we have backpacks. Okay, let's hear some more cameras, please. That's good. Okay, we're going to start recording. If we see red lights. Saw red lights here? Okay, let's see here. Okay, we're recording. We're going to rotate this thing. Okay, so when it's pointing toward you, just be really still. It's going to go around twice. Yeah. Okay, that was number 1. Stay still. Okay, excellent. I'm going to stop this right here. That was our first of 2.
If you run around with it, Paul, can you be everywhere in the room?
You could try to do that in 4 dimensions of ray space, yes. Okay, so I'm going to take it down a speed setting. I'll set it to go around twice, but we're really only going to wait around for it once on this one. And this one here, since it's going to move slower, we're going to have a little less motion blur in our data set, so it'll be slightly sharper, but take a little longer to shoot, so that might have some other things. So we'll figure out which one comes out best. I'm going to start recording here. We're going to hopefully see some red lights. It looks good. Okay, so we're going to go around a little bit slower. We'll let it go around once this time. Okay, I'm going to go ahead and stop it right here. Thank you very much. Yay. Whew. Henry, anything else? We're good? Okay, enjoy the rest of the SIGGRAPH. And see you at the reception. Yeah. I think it worked out great, yeah.